Hey folks, I would like to do another Coulomb's law problem. So in this case here, we're given 3-point charges and we're given the unit distance A and unit charge Q, and we were asked to find the net force on charge B. So I'm just going to work through on charge B here, but for extra practice, you can work through finding the net force on the other two charges as well. So charge B is going to be affected by charge A and charge C. The distance from A is fairly easy to see from right from the diagram, but we are going to need to figure out the distance from C. So let's do that. So we care about this distance in there. This is a right triangle. So if I sort this out, I can figure that that distance is actually A root 17. And then I'm going to go ahead and label an angle in here too, an angle phi right in there. So I encourage you to do this geometry analysis right at the beginning of your problem. And then of course we need some kind of coordinate system. So I'll go ahead and set up a coordinate system based on this diagram right here, and I'll put my positive y upward and my positive x to the right. That gives me my overall coordinate system here of positive j hat upward and positive I hat rightward, because we're going to be expressing this in unit vectors, of course. Okay, so what I want to do then, whenever I'm finding these forces, I always want to draw a free body diagram for the particle that I'm interested in. In this case, it's particle B. So kind of focus in on that particle and draw out the forces on it. So if I look at the relationship between A and B, I see that B is attracted to A. Now, remember, don't get distracted by what the other particles are doing or feeling. You're only analyzing one particle at a time. So particle B is going to be attracted to A. So the force on B due to A is going to be an upward force. And I can label that as the force between particles A and B. And then particle B is going to be repelled from particle C because they're the same sign. So that's going to be off in this direction. And I'll call that the force between B and C. And I'm going to go ahead and label this angle phi. So in your work, don't leave angles unlabeled and open, just knowing it's like that-ish direction. Be sure that whenever you draw your free body diagrams, you have angles that are labeled in your original diagram. So they should always look back to that. And that's the type of work that I'm going to expect to see on your page for the first application or for the first exam. Okay, I'm going to go ahead and put my sign convention on this free body diagram to remind myself of that. So positive rightward, positive upward. And then I can start expressing what this force looks like. So the force on B, I'm going to draw this in unit vector notation, is going to be FBC cosine phi. And that'll be negative I hat direction. And for my y component, I've got force AB, all of that pointing straight up, minus force BC sine phi, and that's in my j hat direction. Okay, so now what I need to do is figure out how to sub in for the magnitudes there. Oh, and something that we didn't do up here when we were doing our looking at our geometry was figure out sine and cosine of phi. That's handy to do right at the beginning, but we can pause and do that now. So if I look at my original geometry, I can figure out what sine of phi is going to need to be. So sine of phi is 1 over root 17. And then, of course, I'm going to need my cosine phi as well. So I have 4 over root 17. The benefit of doing that right at the beginning is that you have your full focus on the geometry, the basic setting up of the charge configuration, and you are not yet using your brain to be doing the force analysis. So you can get best results when you focus on one thing at a time. All right, so now I have my force equation, but it's not in terms of the givens because I haven't yet applied Coulomb's law. So now I'm going to apply Coulomb's law here, and that is to just define the magnitude. So notice I'm not putting a hat on this here. This is the magnitude of force BC. So the magnitude of the force between particles B and C, which is K. Magnitude of particle B is 2Q. Remember, we dropped the signs here. Particle C is 3Q over the distance between them squared. So that's going to be 17A squared. So this can simplify just a bit here to 6KQ squared over 17A squared. All right, so that's that particular magnitude. And now let me find the magnitude of the force between particle A and B. Charge A has a magnitude 5Q. Charge B has a magnitude 2Q. The distance between them is 2A, so that gives me 4A squared. And this is then going to be 10KQ squared over 4A squared, which we can bring down, of course, to 5KQ squared over 2A squared. Okay, so we have both those magnitudes now, and we can put those magnitudes into our equation. So just to highlight what's going on here, right? What we need to sub in for is we're going to need to sub in for the magnitudes here. And those magnitudes I now have, right? FBC, this one, and FAB is that one there. Okay, so let's go ahead and do that. So now I can write out my full FB, and then we're going to sub in for sine and cosine phi also. Phi is not given in this problem. So FBC, it's going to be 6KQ squared over 17A squared times cosine phi, which is 4 over root 17. That is negative I hat. I tend to do it that way. If I put the negative sign in front of the term, it can get lost, especially right adjacent to an equal sign. So this feels safer to me, so I don't drop a sign. FAB, 5KQ squared over 2A squared minus FBC, 6KQ squared over 17A squared, sine phi, which is 1 over root 17. And then that's all j hat. Okay, so that's our final result there. Notice that, and we don't need to simplify. I mean, you can if you really want to, but